All right, guys, so we are doing day 2 of 6.3. We're going to be talking still about binomials, and then we'll get to geometric. Okay, so this is from our example last time with the type O blood. It's our probability distribution. Remember, the couple had the 5 kids. What's the probability they would have? 0 kids with type O, 1 kids with type O blood, etc. Okay, so here is our distribution. Let's pause real quick, and I'm going to have Autumn tell me what shape is that distribution, Autumn.
The shape is going to be right skewed.
Good job. So there we go. There's our distribution there. Okay, let's keep on rolling. Here is a different probability distribution. Ariana, how would you describe that shape?
It's bell shape.
It'd be roughly symmetric, right? Roughly bell shape. Not exactly, but roughly. Whereas this one, what would you say on this one, Jaislyn?
Skewed left.
All right, great. So our probability distributions, our binomial distributions can take a lot of different shapes, okay? And what's nice is the reason I told you we like binomials is because they're formulas. To find our expected value, I want, before we jump to the shortcut, come back here with this. Do you remember when we were doing 6.1 and we were finding the mean and standard deviation of a probability distribution? What we had to do is we had to times the value by its probability and add it all together, right? That was how we got our probability distribution, or the mean of our probability distribution. To get the standard deviation, it was even more complicated. We had to take our value minus the expected value, square it, times it by the probability, do that for each of these and add them up. Kind of complicated, right? Well, check this out. If we have a binomial distribution, regardless of the shape it is, the expected value is just this. It's just NP. N is a number of trials, P is a probability, and that's it. You just times those together and you have your expected value. To get your standard deviation, it's a little more complicated, but not nearly as complicated as what we had to do before. You just do the square root of NP1 minus P. So let's hurry and do this for our draw a heart example that we were just doing. We were going to draw 10 cards and we were going to see, is it a heart or is it a knot? What would the expected value be? You would just take N, which is 10, and times it by our probability of success, which is 1/4. And that would give us 10/4, which turns into 2.5. So our expected value, or our long-term average for the number of wins, would be 2.5. To get our standard deviation, we would just do the square root of NP, but then we also do the 1 minus P. So that's number of trials times the probability of success times the probability of failure, and then take the square root. So to do that, it would look like this. Square root of 10 trials, probability of success was 0.25, probability of failure is 0.75, and so my standard deviation is 1.4. Now, that was a whole lot easier, wasn't it? That's one of the reasons why we like binomial distributions. We have some formulas that are much simpler and much easier to use. Now, they can only be used for binomial distributions. So remember, what was our condition? What is our acronym we have to remember when we're doing binomial?
Bins.
Bins. So make sure you check bins and then you're good, okay? So here's another example. Assume that each of the 21 student in Mr. Hogarth's, whatever, statistics class who did the bottled water versus tap water activity was just guessing. So there's 1 in 3 chance of each student correctly identifying the cup containing bottled water correctly. Do you remember when we did this with the Dr. Pepper and we did, can you tell the difference between diet, or was it no sugar, I think, and like regular Dr. Pepper? And we were seeing if we could tell the difference. This class, they did an activity where they were doing a challenge to see if they could correctly identify the difference between bottled water and tap water, okay? Now, let's say in this case, they actually had 3 cups, but only one of them was the cup they were trying to guess. So they had to taste from 3 different cups. So what they're doing on here is they have 21 students, and they're all going to try to identify whether there's a difference between bottled and tap water. So the probability of success is 1 out of 3, okay? Now, what we want to know is how would we calculate the mean? Using the formula we just learned, you're just going to do NP, which in this case, N is 21. We had 21 students, and the probability of success was 1/3. So we would just times 21 by 1/3, and that would give you 7. So what that tells us is the expected value, or the long-term average. If we did this many times, if we repeated it, then on average, we would get 7 who would guess correctly, assuming they were just guessing, that they couldn't tell the difference. Now to get the standard deviation, we would just use the formula again from before. We would do the square root of NP1 minus P. N was 21, P is 1/3, which means that the complement of that, the probability of failure, was 2/3. Putting that all together is 2.16. This is standard deviation, or average distance from the mean. So again, if we did this many times, then our average is going to be 7, and our typical variance from that, or how much we typically vary from that, is going to be 2.16. Does that make sense how we would use those formulas for your mean and your standard deviation? Do you have any questions on those 2 examples? Now, here's the nice part, guys. If I go to AP Stats formula sheet, I have to like re-download it every time. Do you have to memorize this? And the answer is no. You just need to know where to look and make sure you check your conditions, which again, Sergio just told us the condition is bins, okay? So let me show you that while this is loading. I think my computer is a little slower when I am doing a Zoom call and recording. But let's see this here in a second. Come on. All right, here we go. So probability distribution, if it's just a random variable, here's our expected value formula and the standard deviation formula. Pretty complicated. But if it's binomial, then here is our formula for binomial PDF. That's a particular value. For CDF, you just use your calculator. Here's your expected value, NP, and here's your standard deviation. So you do not need to memorize this. You just need to be able to reference it and check your conditions. Sound good? Okay, let's jump back and let's keep on rolling here, okay? All right, now we're going to be introduced to one of our new conditions, okay? If we think about what we've been saying with independence and how the condition of independence needs to be met, basically we said if we were playing the game of hearts and we didn't replace that card, it would no longer be independent. Well, if you think about in the real world, we never replace people. Like if I'm doing a survey and I ask someone, do we replace that person in a survey? No, it's always done without replacement, okay? So that violates our independent condition. So what we're going to do is kind of come up with a way to kind of get around that, okay? When the population is much larger than our sample, then it's not going to make a big difference, okay? It will still be an approximate binomial distribution, which will be okay. So for example, let's say I was playing the game of hearts and I go to Mindy and I say, draw hearts, and she draws a card and it's not a heart. The probability it was heart was 13 out of 52. But if she doesn't draw a heart and now I go to Darlene and I say, draw a heart, what is her probability of getting a heart? It'd be 1 less, right? So it'd be 13 out of 51. Is that different? Yes. But now let's imagine that there was a much bigger chance. For example, let's say we were working with many decks, okay? And so let's say the probability of her drawing hearts was like, I'm just gonna make up numbers here. Let's make it out of 10,000, okay? So I go to Mindy and the probability that she draws a card is 225,000 out of 100,000, right? That's still 1 out of 4. Let's say she draws a card and it's not a heart. So then I go to Darlene. She still has a probability of 25,000 out of 999,999. Is that essentially the same difference? Essentially it is. Okay, so long story short here, what we're going to do is learn what's called the 10% condition. When taking a random sample of size n from a population of size n, so lowercase n is our sample, uppercase n is our, uppercase n is our population. We can use the binomial distribution as long as our sample is less than 10% of the population. So essentially, we will never sample with replacement. So just make sure your sample isn't too big and you'll be okay. We'll do an example with this here in a second. Here we go. In a survey of about 500 US teenagers aged 14 to 18, subjects were asked a variety of questions about personal finance. One question asked whether teens have a debit card. Suppose that exactly 12% of teens aged 14 to 18 have debit cards. Let X equal the number of teens in a random sample of size 500 who have a debit card. Okay, explain why X can be modeled in a binomial distribution, even though the sample was selected without replacement. So guys, if I went through and I did bins, do we have bins here? Let's get some help from, who haven't I called on yet, guys? I think I've gotten about everyone. So I'm just gonna ask Micah to help me on this one. Mike, are you there?
Yeah.
Okay, what is B for bins?
It means if it's binary, so it has two outcomes, a success and a failure.
Does this
And
situation have that?
They either have a debit card or don't have a debit card.
There you go. We're going to skip I. N, what does N stand for?
A set number of trials.
And do we have that here?
Yes, 500.
Okay. And then S, the probability of success. What was the probability of success?
12%.
Okay. So then we've met the requirement for BNS, but not for I. Okay. So I is independent. Technically, we're asking people without replacement. So is that independent? No. But what we learned on this last slide was as long as our sample is less than 10% of all of the population, we're okay. So who is our population?
US teenagers.
Okay. We asked 500. Is that less than 10% of all teenagers? Well, the way you can check that is just timesing our sample, which is 500 by 10. If we times 500 by 10, we get 5,000. Is there more than 5,000 US teenagers? Yeah, definitely. So 500 is less than 10% of all US teenagers age 14 to 18. So since we've met the 10% rule, we can just keep moving. We can assume that the independence requirement was met. So now we want to find the binomial distribution to estimate the probability that 50 or fewer teens have a debit card. If we're doing 50 or fewer, guys, is that going to be a binomial PDF or a binomial CDF? Are we doing a particular value or are we doing a cluster of values?
It'd be
PDF.
because
Sorry, we had two people talking. Was that PDF or CDF?
I'd say it would be CDF because you have 50 or fewer. So it'd be
We have a
both
range, a
50.
cluster of values, right? Awesome. Thank you for speaking up. So let me show you how to do that. I'm going to go on my calculator to binomial CDF. So we were going to talk to 500 people. The probability they have a debit card is 12. and we're going to go 50 or less. It included 50, right? It was 50 or less. And so there would be about a 9.3% chance that we would get 50 or fewer. Let's check that here. Nice. We did that. Now notice on here, this is how you're going to show your work, is writing it out like this. You're not going to have to show it for 50, 49, 48, 47. That'd be way too much work. You just need to write out what your values are. So they didn't just put in 500.12. They actually said the trials was 500. The probability was that, and our X value was 50. So you have to be specific. Okay. All right. This next one, this topic is not required. So guess what we're going to do with it? We're going to kind of skip it. I might go over it super fast. We're mainly going to see this in chapter 7. But the big takeaway here is that as your sample size increases, your distribution is going to look more normal. Okay. So for example, right here, this was a binomial distribution, but only with a sample of 10. This was a binomial distribution with a sample of 20, and then this was a sample of 50. Notice the shape here with 10, it kind of looks skewed to the left. But as the sample size increased, this looks approximately symmetric. So one of the things that we're going to hit really hard in chapter 7 is that with a larger sample size, our distribution looks more normal, okay? In chapter 6, it's not that big of a deal with binomial. That's actually not something that AP is testing on, but they will test on that with sampling distributions, which we'll see there. So they come up with this large count condition, which is basically a way of making sure that your samples were large enough to claim to be approximately normal. It basically is just that your expected number of successes and failures needs to be at least 10. Okay, so we might see that a little bit, but mainly we're going to focus on other things. So just to show you a quick example, could we assume that this example we just saw was approximately normal? Well, we're going to take NP and times it together, and we get 60, which is greater than 10. We'll do N minus 1 minus P, and we get 440. Since those are both greater than or equal to 10, we can assume that this is an approximately normal distribution. Therefore, we could use norm CDF. Okay. And then we could even go and do some calculations using norm CDF instead of using the binomial. Now, what's interesting here is that our answers might be slightly off because it's not exactly normal. We got like 9 point something, they got 8 point something, but it's still going to be similar. Okay. So I'm going to pause there. That is what we needed with binomial random variables. So what you need to know about them, for the most part, let me go back to our formula sheet, is this is how you calculate for a particular value. This is your formula. If you're doing a cluster, then you're going to do your calculator, but make sure you label. Here's your expected value. Here's your standard deviation. Now, what you need to memorize that's not on here. First off, bins. You need to be able to say if it's binomial or not, and that's something you have to memorize. We are going to, in bins, we're going to violate the independence condition because we don't sample with replacement. So the way we get around that is with the 10% rule. Your sample needs to be less than 10% of the population. Okay. And then as far as that normal thing we just looked at, that's not going to show up on the test, but it is something we're going to see in chapter 7. So do you have any questions on binomial distributions? Questions? We are going to take a 2-minute break. 2 minutes so you can stand and stretch. We're going to come back and do geometric. It'll be pretty quick because it's very similar to binomial, just one slight difference. And then we'll be done with chapter 6. Yes. So 2 minutes. You ready? Go get a snack. Stand up, stretch. I'll be back in 2. All right, was that 2 minutes? I think we're good, right? Oh, I should have paused the recording. That was lame. People are watching this are gonna be like, 2 minutes, Solver. Do you know what's actually kind of funny? Was last time, I forget who was on, but there was someone who was on and I was just waiting for them to like get off because they were still there. And so I busted out my harmonica and started playing songs. And then I realized after I was done, I was like, oh, this is recording still. So if you go back and watch the recording, you can hear me play a song on the harmonica. I'm not very good though. All right, are we back? I need everyone in the chat to say ready to go or to unmute and say it so I know that we're ready to go. Ready to go. I'll be Hiram and put just that. Ready to go. All right, we ready? Let's do it. Okay, you guys are great. Let's go through. So I believe I'm still sharing my screen. So can you guys see this? Binomial or geometric. Okay, a geometric setting arises when we perform independent trials of the same chance process and record the number of trials if it takes to get one success. On each trial, the probability of success must stay the same. How is this different than a binomial? In a binomial, you know in advance how many you're going to do. You're going to say, we're going to have 5 kids, or we're going to do this trial 80 times. And then we'll look at how many successes we get. Whereas this, you go until you get a success. Now, sometimes that success is actually what we would think is a failure, right? For example, a basketball player is going to shoot until they miss. Now, until they miss, you would think that would be like a bad thing, right? But you're going to think of it as they're going to make. How many can you make until you miss? Okay, so that's geometric. The number of trials y it takes to get a success in geometric setting is a geometric random variable. The probability distribution of y is a geometric distribution. Possible values are 1, 2, 3, so that we're working with discrete. Now, here is your formula here. It's actually pretty intuitive. For example, let's say I am a pretty good basketball shooter, okay? What's the probability that I'm going to go and shoot until I miss? Then I'm going to say, what's that probability of getting that, or like the expected value? I could figure it out using this formula. 1 minus p is a probability of you failing, right? And the p is a probability of you making it. And you are going to fail until you make it. Okay. Let me do an example and it'll make more sense. Okay. These teachers, I can't pronounce their names. Mr. Lochel's class decides to play the lucky day game. A student will be selected at random from the class and asked to pick a day of the week. Then your teacher will use technology to randomly choose a day of the week as lucky days. If the student picks the correct day, the class will only have one homework problem. If the student picks the wrong day, your teacher will select another student from the class at random and repeat the process. The game continues until a student picks correctly, and y is the number of homework problems that they get. Does that make sense? So I would go to Sergio and I'd say, hey, Sergio, choose a day of the week. 3, Wednesday? Sure. He says Wednesday because his mouth is full. He's snacking over there. And I would draw on my wheel. And if it was Wednesday, we'd say, it's your lucky day. You only get one homework problem. If it didn't work, then I would go to the next one. I'd say, Lily, choose a day of the week. And she would say,
Monday.
Monday. So I would spin it. And if it was Monday, then we'd say, boom, you only have 2 homework problems. If not, it would keep going and going and going. And theoretically, how far could this go? It's like Moana. No one knows how far she'll go, right? See that reference there? Okay. So Find the probability that the class receives exactly 10 homework problems. So if they had 10 homework problems, how many times did they guess incorrectly? Help me out here, guys. That means that they had, I think it would mean that they got it right on the 10th person. So that means they would have 9 failures. And then on the 10th, they would get it right. Because I think if the first person gets it correct, they just have 1. So if the 10th person gets it correct, it's 10. So what that means is we're going to have 9 failures. What the junk? That's not right. Don't look at their work because they're stupid. Where's my pen? So what's the probability that y is 10 is what the question was we're asking there, right? Where did that go? Stupid. Okay. So this is a geometric because you go until you have a success, which in this case is that they get it right. Okay. So the probability of getting it right is 1 out of 7. Okay. And what we're looking at is what's a probability that they get it right on their 10th time. Okay. So we're going to use this formula right here. The probability of getting 10 is going to be, well, what's the probability of getting it wrong 9 times and then getting it right on the 10th time? So I'm going to write this out like this: probability of getting 10. So if 1/7 is a probability of getting it right, what's the probability of getting it wrong? That would be 6/7. We're going to get that 9 times. And then the probability we finally get it right after that would just be 1/7. So I'm going to get out my calculator. We're going to do 6/7 to the 9th power, and then we're going to times that by just 1/7. I'm going to add a decimal in there to make sure it gives me a decimal, and that's about 3.6%. Okay, so there's only a 3.6% chance that they're going to get 10 homework problems. Now I could figure that out with other ones and say, what's probability you only get 1 or probability you only get 2? But these are going to be PDF questions. Find the probability that y is less than 10. Now we're not doing a PDF. What are we doing?
CDF.
Thanks, Lily. Sergio, you're okay? I think his computer just fell over. All right. So the way that we would do this is I would get up my calculator. And let me just show you that this worked for the first example. We're going to go to the same place we did for binomial PDF, but now we're going to go to geometric. And if you come down here, you have to go a little bit further. Here's geometric, PDF, and CDF. So for PDF, the probability of success was 1 out of 7. We said, what's probability we get it on the 10th day? And they would say, boom, same thing we got, right? But now we're saying what's a probability that it's, let me check the question. Was it 10 or less? No, notice here it's just less than 10. So that less than 10 means that it's going to be 9 or less. Okay, so you have to be really careful with how you do that. So like go to my calculator, we're going to go to our distributions and go down to geometric distributions. And we're going to do a CDF because it's a cluster. So again, the probability of success was 1 out of 7. And we're going to go all the way from 1 because that's the lowest you could be here. You couldn't have 0 homework questions. And it said less than 10, so that would be 9. And that would give us 75%. So there's a 75% chance you're only going to have 10 or less. But theoretically, you could go on forever. It could be like going on for infinity, okay? All right, that is an example of how you do that one. They went through and they showed you how to do this, like for each scenario. That would just, and that's maybe a good thing to think about. What's the probability you get it the first time? Well, that'd be 1 out of 7. The probability you get it the second time, well, that means you got it wrong and then you got it right. So that'd be 6/7 and 1/7. Third time, you'd get it wrong twice and then you'd get it right. And you see the pattern there, how it just keeps building. If you add all of those up, you get about 75%. Okay, so that's the difference between a geometric and a binomial. Yeah, so when you said, where did they get 500? Was that looking at the solution here? That was just, this solution was from a different problem and they didn't fix it because they're sloppy. So sorry, I should have caught it. Okay, I just showed you how to do it on your calculator. Again, it's PDF for a particular value. It's CDF for a cluster of values. Okay, so now your geometric distribution, since it can technically go on forever, it's almost always going to make this skew to the right shape. Okay. Now to get the expected value, let me show you your formulas here. This is your formula for expected value and standard deviation. All you have to do with the expected value is just do 1 over P. So the probability of me choosing the right day of the week was 1 over 7. If I do 1 over that, it's going to flip it, so it just turns into 7. Wasn't that easy? Geometric's great. As far as the standard deviation, you do the square root of 1 over P divided by P. I don't know how they calculate that, but don't question it. We'll just go with it. Okay, so let's do an example here. I'm going to have a reader read this because I'm tired of talking. So let's have Mindy. She's right there. Go ahead, Mindy.
A local fast food restaurant is running a draw a 3 get it free lunch promotion. After each customer orders, a touchscreen display shows the message, "Press here to win a free lunch." A computer program then simulates one card being drawn from a standard deck. If the chosen card is a 3, then the customer's order is free. Otherwise, the customer must pay the bill. Let X equal the number of customers it takes to get the first free order on a given day. Calculate and interpret the mean of X.
Thanks, Mindy. So we did this before where we said, what's the probability if we had a group of like 50 or 250 that like 80 of them got it or something like that, right? In this case, we're just going to have a customer play it over and over and over again until they win. So how many times would you have to play this game until you got it? Well, let's just talk about this real quick. What's a probability they win the first time? What's a probability in a deck of cards you choose a 3? There's 4 out of 52, right? 4 out of 52. Good. Mindy is signing to me. Good thing I know sign language. Very little, very little. Okay, now, what's probability that they get it the second time? Well, that would be they lose, which is 48 out of 52, and then 4 out of 52, and then 3, and then 4, and it kind of keeps going like that, right? Well, we want to know what is the mean and the standard deviation. So to get the mean, let's just take that 4 out of 52, which is 1 out of 13, and flip it over, and it should give us 13. Isn't that nice? 1 out of 13, flip it over, gives us 13. That's it. To do the standard deviation, we're just going to take the formula that they give us and plug it in, and we get 12.49. So that just means that we would plug that in, 12.49. Our average distance from 13 is 12.49, which is almost 13. So there's a lot of variation here, okay? So even though we're expecting it to be around 13, it typically varies anywhere from like 1 all the way to 26, right? So it's a little crazy. All right, and that is it for geometric. So let me actually show you on your formula sheet here. Here is your formula for calculating probability with geometric. Here's your expected value. Here's your standard deviation. What I need you to do is we're going to take 30 seconds, and I need you in your brain to say, how is a binomial distribution different than a geometric? What is a difference? And then I'm going to call on one of you, okay? So be thinking. And Sergio, you got called on. What is the difference between binomial and geometric?
Isn't it a binomial is like one failure, yes or no, and like derivations of that, and geometric has parameters? I don't know.
So what's the 4 letters we have to know for binomial?
It's bins.
Bins. So it's binary, independent. What does the N stand for?
Uh,
So N is number. It's a fixed number of trials. So that's what makes binomial binomial is you have a fixed number of trials, okay? S is probability of success, that's the same. So in geometric, it's actually the same 4, except we're gonna replace N with T. This is gonna be bits. And that T for trials is basically gonna be trials with a question mark. We're gonna go until you win, okay? So with a binomial distribution, it's just like, hey, we're gonna do this 10 times. Let's see how many times we win. With geometric, it's like, I'm gonna do this until I win. Does that make sense, guys? So what we're gonna do, I gotta talk about 2 things and then I'll let you go. So this is gonna wrap up 6-3. We are going to review on Tuesday and test on Thursday. Now, one of the problems is that our online software is being funny. It only lets us go at a semester at a time. And so we got to the end of the semester and they're like, hey, if you want to use this for next semester, you have to unlink it and pair it for this semester. So I unlinked it from last semester and then I couldn't link it this semester. So I'm having some technical difficulties. I'm hopefully going to get that resolved today. If not, I'm going to assign you textbook problems to be working on for your homework. So I will be in touch with you soon, but I need you guys to be studying and preparing so that we can review on review on Tuesday so we can test on Thursday. What questions do you guys have? Any questions? Go on once. Go ahead.
Work instead of doing the homework online.
Can you say that again, Darlene?
You're gonna assign us bookwork instead of doing the homework online, since the Macmillan learning is like down.
Yeah, so if I can figure out how to get it up and running by today, it'll be online. If not, I'll send you the textbook problems for you to do.
Okay.
Did that answer your question?
Thank you.
You're welcome. Any other questions?
Yes.
Okay, I'm going to stop recording. See, we don't need that.